There are different advantages and disadvantages of every scheduling algorithm. So we try to create multiple queues based on the priorities. There are different scheduling algorithms that we can use. So this is the one that is mostly used, where we have basically created multi-level queues for scheduling, and each and every queue would have their own priority or scheduling algorithm. So that we discussed, and further we go for feedback mechanism, multi-level feedback queue, in that each and every algorithm scheduling algorithm is used for different level of queues. So we try to enter the jobs into one particular queue, and based on their response or behavior, based on their CPU burst, we are shifting them to higher priority queues or to the lower priority queues. So in the previous example, we discussed about that a particular process, if it is you are able to basically your operating system is basically able to execute this within 8 quantum, then it will be finished here. If it requires more quantum time, then it will be moved to a lower priority queue. And if further it is not able to finish in that particular quantum of time, then it will be sent to a lowest priority queue. So the combination of these two basically is used. This along with this is used for actual operating system, where the tasks are basically moved up and down, which also takes care of the aging factor of the processes, so that it should not remain lying for many years without being actually processed. Because we use our desktops or computers, so we know which task is you are running. You can see why it is not responding, but on server no one is actually monitoring other than system admin. They may actually skip a particular job is there which is lying for so many hours. And normally what happens is the low priority task and maintenance is done at lowest peak of the server. So there are different things, but related to the processes, this is the procedure, like how they are basically scheduled to give or to be allocated to the CPU. So the whole job is to make your CPU 100% utilized. And we saw in our previous lecture that normally 99% of our CPU is free and idle. And the whole job of this, basically the free, all those CPU cycles are going free, and we can put and sell those CPU cycle to some other agency so that they can use your computing power to do some kind of simulation or their work. So that is basically contributing towards grid computing environment or mobile computing environment. You can sell that basically. So then we discussed about thread scheduling, and then now today we are moving toward multiprocessor scheduling. So in multiprocessor system, we know there are multiple CPUs. Now, multiprocessor is very broad term. There could be multiprocessor on a same board. They are multiple processor on a same chip. Those are called multi node basically CPUs. And then we could have a networked multiprocessor system where more than one computer is connected through LAN, and they're working on a single problem. So the definition is very broad. How we can perform the scheduling on these different environment is a challenge basically. There are different type of environments when we have homogeneous processors. So their capability, their RAM, their cache, their register, and their style of coding, the assembly, and their basically, if I say the assembly language statements are all same. So they have same type of structure. So those are homogeneous processors, which are something similar with the performance. But when we have to schedule the jobs, there are two type of things. That is, one is called asymmetric multiprocessing, In asymmetric multiprocessing, one processor is basically the master node, which access the system data structure, IO, and make the decision about scheduling, and all other processors are just following what master has given. Uh, this is something similar to like what is happening in Hadoop. We have a single node which is managing the whole in network system. This is kind of analogy is there. So asymmetric multiprocessing, I'm talking about on a same board, we have multiple processors and one processor is leading the other processors. And whereas in symmetric multiprocessing is when we have multiple processors, rather than having one processor as master for scheduling something, each processor would schedule its own queue. So each would have its own queue. So each processor would be doing self-scheduling of all the processors that are in the common ready queue. So each has its own private queue for the ready processes. Now, if we select, now there are two options. One is basically the symmetric multiprocessing. There are two policies which are there. Each processor is self-scheduling but have a common ready queue. So each would have a common ready queue. And the other is basically each has a private queue for the ready processor. So this is something which is there. Symmetric multiprocessing is each one is capable of dealing with its own set of jobs. So this is the difference between asymmetric and symmetric multiprocessing. All modern operating systems are following this symmetric multiprocessing scheduling. There are two strategies. One is each processor is self-scheduling and all processes in common ready queue. And whereas the second strategy is that each process has its own private scheduling for the ready queue. So each of the strategy would have some advantages and disadvantages. So the first one, if we select the first option, we have possible race around condition. Now, what is race around condition? This term would be very, very important for operating system, because we in operating system we prefer that multiple jobs should run concurrently, and we know that a process is split into threads. So when we talk about threads, they have common sharing of the data and the space. So when it is basically sharing, then we don't know which process is going to take lead and would execute that particular data space. So let us suppose we have two threads, T1 and T2. T1 is running its own instructions, T2 is running its own instructions. Now our operating system allows for preemptive scheduling. In preemptive scheduling, this may happen that T2 has not written anything into X, and T1 has not written anything into X location, and T2 is actually trying to read it. Now, it may be possible that T2 has not written anything into it, and the context switching has been performed, and T2 started executing, and which would try to read from this particular variable. So some conditions are happening because of this, because there are multiple processes. Those are trying to uh, fetch the information from the same memory spaces or from same variable. So the order would always matter. Like if the order of the instruction which are executed change because of the context switching, then that condition would be called race around condition or race condition. This is not only happening in the software case, but it also happens for the hardware cases also. So I will discuss more on this and would try to make it more clear when we go to the next chapter. Uh, so what is happening when we have multiple threads in the queue? Because we have a common queue, it may be possible that more than one core tries to access the same thread, and they both try to acquire and start working on the same thread. So basically that would be the repetition of the work, and also it may be that inconsistent the inconsistent state of data may be there. So let us suppose T2 is basically incrementing x. So x is equal to x plus 1. So if this core and this core both started working on T2, they may increment this location x by 2 times. Rather than just adding it by one value, it will be added 2 times, because T2 would core 0 would also add 1 to x, and core 1 would also add 1 to this particular variable. So this particular condition where your data is inconsistent due to the context switching is called race condition. If we select the first option, we have possible race condition on the shared ready queue. Therefore, we must ensure that two separate processors do not choose to schedule the same thread, and that thread should not lost from the queue. And we could use some locking mechanism to protect the common ready queue from this race condition. So I hope this is clear to you that what is race condition, because each and every core would be racing to get more threads. So in that situation, it may be possible that they try to acquire multiple cores, try to acquire the same thread. So this is kind of, we need some mechanism of locking. When one core is accessing a particular location, the other core should not be given access of that particular location. This is the problem with preemptive scheduling. When we have preemptive scheduling, it means that there are more than one processors or processes are trying to acquire the same location. In non-preemptive, once the process is started, it will get to the termination of it, because it is never preempted. So that's why non-preemptive kernels are much simpler than preemptive kernels. So I'll get back to it more on this thing. This is very important. The second option is that permits each processor to schedule threads from its own private queue. So when we have each one is having own private queue, then there is no problem of racing condition, and they can actually basically work on the tasks which are given. So this particular thing is mostly used in modern operating system. Uh, then we have multi-core processors. So if we say multi-processor system, we have different CPUs working together. When we talk about multi-core system, so in multi-core system, we have more than one core on a same processor. So there are different cores which are there. So let's suppose you have two cores, so it's dual core system. So in dual core system, each CPU would have two cores. Now each core would, we have to manage the scheduling between them also. So how that happens, so let's discuss about that. Normally what happens is the processor accesses the memory. It spends significant amount of time waiting the data to become available, and this is called memory stall. Whenever a processor is working on some particular, waiting for some memory thing, or accessing the memory, because when we go for catching the data, it should be visually, you should be able to visualize how the data would be actually asked. Whenever your CPU is requesting some data, so it will convert into a system call. That system call would go to the device driver. It will ask that to do certain task, and then device driver would actually ask the disk controller. Disk controller would then search for that data. If it is not in the memory, I'm talking about if it is not in the RAM, so it goes to the disk controller. Disk controller would actually run your hard disk, and then from there it will try to find out, look at the index table, then find out, retrieve the information, and then send it back to the device controller, and from device controller it will go back to the CPU. So this is a significant amount of time which would be happening. That's why this is also because CPUs are running much faster than the RAM or your basically the storage devices, because the storage devices are bound by the speed of transistors. If you are aware about hardware, so there is always a lag by which your information is transferring. So if I talk about, I'm just going little into that detail. Let us suppose you want some data. Now that data would come on a line which would be carrying some information. Now information would come in the form of bits. So let us suppose this, then this, then this, then this. Now what is data? 1 0 1 0 1, and it may be here 1 1. So this is the information how it would be traveling from one place to another place within your computer system. So now how this is actually represented, it is represented using signal. So signal is what? It is voltage. So it is 0 volt and this is 5 volt. Either your circuit is plus 12 or plus 5 or plus minus 3 volts. So all these are basically the voltages, those are happening. So all these are used to basically represent zeros and ones. So whenever there is this spike is coming, it is not actually like this. So it will take some time to go up and take some time to go down. So the actual signal would be like this. So this is your one here. So this time is the delay basically to actually become from 0 to 1. This is the delay that would happen at your transistor output. So this limits the speed of the hardware. So this speed, all the transitions are happening from low to high, high to low on your hardware part, basically limits the performance of your hardware, whereas CPU is just basically working on at higher clock speed. So what I mean to say is your processor is running much higher than your memories, and so whenever your processor executes something and need some memory location, access some want to access some data, so there would be a significant amount of time that it would be actually going for the wait state. So what would happen is the memory stall. Memory stall is when your CPU is waiting for some data to be available, and in that case memory stall could also have memory stall can also occur because of cache miss. So cache miss is basically because your computer your CPU is picking the instructions from the cache and executing it. So the whole process is we put the data from secondary to RAM, then from RAM to cache, and then from cache to the registers. So whenever your CPU is executing something, the first thing it will look for the instruction into the cache. If it is not there, then it will go to the RAM, then it goes to the secondary, and from there it will pick the data, and then this is how it would happen. So in case your cache is the instruction is not available in the cache, then again this is a memory stall case for your CPU. Then so basically to take the advantage of memory stall, what is happening and how the new processors with multi-core system are coming, that is called multi-threaded multi-core systems. So if you have heard of that concept of Intel processor that comes with hyper-threading, that hyper-threading is basically means that your CPU, your processor or your core is able to take advantage of these memory stall times. So how they are doing it now, normally what happens is whenever you are running a thread on a core, let us suppose core 0, so thread would have some computation part, and then we have a memory stall cycle. So it will have two cycles. So compute then wait, compute then wait, compute then wait means it is waiting for the memory the data to become available, and then it start computation. So when this is happening, what is the remedy for this? This all 50% CPU utilization is going waste. What is done here, rather than running one thread, two threads are being executed. Now how they do it, within a core there are two hardware threads. So we discussed about software threads, that we create smaller processes, lightweight processes, and those are executed just like your processes we are discussing about the process. Okay, but in hyper threading or multi-threading system, hardware threads are given. So the hardware thread is basically which has its own instruction pointer, register set, and this appears as a logical CPU. So further fine graining is done. So in this, we have, you can see the processor. It has core 0, core 1, core 2, core 3. It has 4 cores. Now each core would have 2 hardware threads. Those hardware threads would be sufficiently able to run a particular job. So each would be a logical CPU. They would be sharing the resources, but they would have some independent things, and they would be actually sharing some the computation part, but they would be 2 threads simultaneously in the memory or instruction register set. So basically what has been done, 2 set of CPU registers has been created. Actually, keep this information. Okay, so now next case is when your rate monotonic would actually miss the deadline. So what is happening here? P1 is 50, P2 is now 80. Execution time is 25 here. Execution time here is 25, and then it's 35. Now what would happen? Because the priority of this is smaller, so P1 would start executing and it will take 25 milliseconds here. I'm changing the time of execution because I'm going to discuss about the utilization of the processes here. So utilization of the process is the time divided by its period. It's Ti by Pi. Okay, so we will calculate this. This is 0.5. Okay, here, and for this is we have to calculate. Now let's see, P1 is allocated and it will start executing. Then after that P2 would start executing, and it will take how much time? It will start executing till the time another P1 is there. So at this particular time P1 would be allocated to the processor, so it ran only for 25 milliseconds. Again P1 started running, so it ran for 25 milliseconds. After this your P2 started. Now P2 is actually basically running for, left with your 10 milliseconds, so it actually started running. Now what has happened here is that your basically the deadline for P2 process has been missed. So P2 has missed. So even with rate monotonic, we see that your deadline has been missed. Now why this has happened? So let us compute what is the scene here. So in this case, in the previous case, the computation is Ti over Pi. What is T? Ti is 20 over Pi is 50. So it is 0.5. The CPU utilization is calculated by this. Then P2, the CPU utilization for P2 is 35 divided by 100, 5. So how much is your computation? It is 0.4, sorry. It is 0.4 here. So how much is the computation? It is 0.435 equal to 0.75. This is the utilization for this particular process. So CPU utilization here is this. Now what about here? Here the Ti divided by P1 is 20 divided by 50. So it is again 0.4. And the second is T2 divided by P2 is basically giving us 35 divided by 100. How much it is? Again 0.35. So again the computation is, the CPU utilization is 0.75. Now what we see here, we have CPU utilization of 0.5 plus your would be 35 divided by 80. So it will come, the total would come around 94. So here the CPU utilization for this is 0.94. What we saw is when the computation is smaller, when the CPU utilization is smaller for rate monotonic, it is able to successfully schedule those processes. When the CPU utilization is higher, then rate monotonic start missing the deadline. So what I'm saying here is this is the worst case CPU utilization that can happen for RM. If the CPU utilization is higher than this particular number, then you are certainly going to miss, or your scheduler would certainly miss the deadlines. So if we say that we have 2 processes, those are running at 75 processor, and best the approximately 69% as the number of processes are approaching. This is the 69% is the maximum CPU utilization that we can take from the RM algorithm. If your processes require more CPU utilization, RM is going to miss the deadline. So if I say my deadline is 30 by 40, and then I have my deadline 80 by 100, so how much it is? It is more than, 0.8. Then we have something like it is too much, then 7, it's more than 100%. So this could never be executed. And even the tasks which are require higher than 69% of CPU utilization, they may not be, scheduled by your RM algorithm. It is going to miss the deadlines if the utilization is higher than. This is worst case, where as the number is growing, this is basically going down, but we always need to check. So this is a number where we can always check for whether our jobs will be scheduled or not. So the CPU utilization is never 100% with RM algorithm. Now, moving toward the earliest deadline, priorities are basically assigned as per the deadline. So if the deadline is close, then that has a highest priority as compared to RM algorithm, where the priority was attached based on the period. So priority would be checked based on as it enters into the queue, basically. Okay, so that is how we